In this video, we are going to look at the gradient, divergence, and curl of curvilinear systems. This is our overview slide, which we'll spend a few minutes on before we do each topic in more detail and with more examples. So first, we just have a quick review of spherical to Cartesian coordinate conversions, as well as the scaling factors over here for the r variable, the phi variable, and the theta variable. Then we have our cylindrical to Cartesian coordinate conversions with our r, z, and phi scaling factors. Then we'll talk about the gradient and curvilinear systems. And for a scalar function phi, the gradient is equal to 1 over the scaling factor, the partial derivative of phi with respect to the ith coordinate in the ith coordinate direction. And then we have that worked out for spherical coordinates and cylindrical coordinates. Then we'll look at divergence of curvilinear systems, which is equal to this formula here, which looks a little complicated, but it's not too complicated. And we'll look at that, how it goes and gets converted to spherical and cylindrical, as well as examples of each of these. And then finally, we'll have the curve and curvilinear coordinates. And here is the Levi-Civita notation, and then I also have it here as a determinant, which I find easier to remember. As we go through each topic, I'll keep these spherical and cylindrical formulas here for your reference, and this should be a pretty quick video. It's mostly just about how to use these formulas. Our first topic is gradients. So in general, for a curvilinear system, this is how we calculate the gradient. And we have the formula here for spherical and cylindrical, and I'll just show you next how we use this general formula to get the specific formula for spherical, and then you can try out cylindrical on your own. But let's take a look at this formula. So I've copied it here. I expanded it out by doing the implied, well, I guess because of these i's, doing the implied summation. So I have 1 over h1 d phi dq1 in the q1 direction, 1 over h2 d phi dq2 in the q2 direction, plus 1 over h3 d phi dq3 in the third coordinate direction. Looking at this, I'm going to start plugging in things for the spherical coordinate. My first coordinate is with respect to r. So 1 over hr d phi dr in the r direction. My next coordinate I'm going to use is my phi, so 1 over h of phi, I'm going to call this phi now, d phi d phi in the phi direction, plus then my last coordinate is theta, 1 over h theta d phi d theta in the theta direction. Now, hr in spherical coordinates is equal to 1, h phi is equal to r sine theta. Oh, I'm sorry, here I switched these two. Well, that's okay. We can do theta first. So h of theta is 1 over r d phi d theta in the theta direction, and last we'll do phi. So 1 over h of phi is 1 over r sine theta d phi d phi in the phi direction. So just kind of multiplying the 1 out, I get this formula, which is exactly what we have here. So you can use this formula again to try the cylindrical coordinates or any other coordinate system someone may give you. I have a quick example. If our scalar function rho phi z is equal to rho sine phi, I use this formula here, which I didn't copy it down. I'll use this formula here for my gradient and cylindrical coordinates. So first, I need d phi d rho in the rho direction. I need d phi dz in the z direction, and then 1 over rho d phi d phi in the phi direction. Now I'm going to plug in my phi. So I have d rho, and then I plug in my phi, rho sine phi, again in the rho direction. Here I'm going to plug in my phi, so I have d dz, my rho sine phi in the z direction, and then 1 over rho, and then d phi, and then I'm going to plug in my phi, rho sine phi. in the phi direction. So I start with this term here, and I'm going to take the derivative with respect to rho. So I'm going to get sine of phi in the rho direction. Here, the partial derivative with respect to z is 0. So I have 0 in the z direction. Over here, I need to take the partial derivative with respect to phi. So I have 1 over rho cosine of phi. And then these two cancel out. So my final answer is sine of phi in the rho direction and cosine of phi in the phi direction. The next topic we have is divergence in curvilinear system. This is the general formula here, which looks complicated, but it won't be. And this is what it is translated to spherical coordinates and cylindrical coordinates. Again, I chose my spherical coordinates to show how this general form can be applied to spherical coordinates to get this formula here. So again, you can use this general form and you can take the cylindrical coordinates and check that yourself, as well as doing other curvilinear systems. But this one here I'm going to show you for spherical. So I copied my general formula right here. Then the first thing I do is I need 1 over h1, h2, h3. So hr is 1, h phi is r sine theta, and h theta is equal to r. So multiplying the 3 together, I'll get r squared sine theta, and that's what this is over here, this factor here. The next thing I need to do is with respect to the first coordinate, a1. So that's the r coordinate. So I'm going to take h2 and h3, so the things that are not the first coordinate, but the second and third. So that'll be r sine theta and r. So that's going to be r squared sine theta, that's this here, times my r coordinate of my a vector, partial derivative with respect to r. I do my next coordinate, which here I named as phi. So I need h1 and h3. So in other words, the ones that are not phi. So that's hr and h theta, so that's 1 times r, and I get r times a of phi, partial derivative with respect to phi. And then finally, my last coordinate is going to be theta. So this is a theta, the theta coordinate of my a variable, a vector. And then h1, h2. So that's 1 and r sine theta. So it's just r sine theta. So this is my formula. I did some algebraic simplification to get this last line here. So to do an example of divergence in spherical coordinates using this formula here, let's use the vector r squared in the r direction, 0 in the phi, and 0 in the theta. So we're mostly working with this portion here. So del dot A is, where's the spherical? 1 over r squared ddr r squared times our r variable, which will be r squared. And then the rest is going to go to 0, since this is 0, our a theta and a phi are 0. These two will be 0. So looking at this, one thing that you don't want to do is cancel this r squared with this r squared and then say ddr is 2r, because that would be incorrect, since what you would need to do when you take the partial derivative is the product rule. But actually, you don't even need to do the product rule. You just need to multiply it out. So 1 over r squared ddr, r to the 4th. So 1 over r squared, the derivative with respect to r is 4r cubed, which will give us 4r. And again, I guess this point is over here as well. You don't want to cancel this r squared with this r, because here you have a function of r. So if you took the partial derivative, you would need to use the product rule, and it's not as easy as just canceling it out. But you don't even need to use the product rule over here, because you're just going to be multiplying this times another function. I have one other example for divergence in cylindrical coordinates. So we're going to use this formula for divergence. Again, it comes from this general form. Plugging all this in, you can derive this formula. And we're going to use this formula on the vector A, where we have rho times 2 plus sine squared phi in the rho direction, plus rho times sine phi cosine phi in the phi direction, and 3z in the z direction. And I did some algebra here so that in the rho direction I have 2 rho plus rho sine squared phi. In the phi direction I have rho sine phi cosine phi. And then in the z direction I have 3z. So my dot product is 1 over rho, so I write 1 over rho, dd rho, of rho times my rho coordinate. So this is rho times this coordinate here. So I'd have 2 rho squared plus rho squared sine phi. My next term is 1 over rho, so I write my 1 over rho, dd phi of my phi coordinate. That's over here, rho sine phi cosine phi. And finally, I have ddz of my z coordinate, and that's 3z. So here I have 1 over rho, take the partial derivative with respect to rho, so I get 4 rho, 2 rho sine squared phi, and now I have my rho, and I factored out this rho, so rho over rho, and then partial derivative with respect to phi is minus sine, and again, now we need the product rule, minus sine squared phi plus cosine squared phi, and over here partial derivative with respect to the z is going to be 3. By the time you simplify everything, you get 8. The last function we have is the curl, and the formula I like to use is this determinant form because it essentially looks a lot like the regular curl formula, except first you divide by h1 times h2 and h3, and then on the top you need to multiply by the scaling factor, and also on the bottom you need to multiply by scaling factors. So now we'll use this curl definition on cylindrical coordinates. So we're going to use that on the vector 2 in the r direction, 3 in the phi direction, and 0 in the q direction. So del cross A, the curl, is equal to, now we multiply 1 over h1, h2, h3. In cylindrical, hr is 1, h2, hz is 1, and hv is rho. So we just get rho, 1 over rho. Here I have h1 times q1, so that's 1 times the rho basis vector, dd rho, and then h1 times a1, again h1 is 1, and a1 here is 2, so 1 times 2 gives me this 2. Next we have h2 times q2, so I did rho for the second coordinate, so I'm going to have rho times the basis vector, phi, and then dd phi, and then h3 times, that's rho, times a2. So that's going to be rho times a2, so I'll have 3 rho. This should be a rho. I don't know if you could tell. And then finally, h3, which is just 1, times q3, that's the z direction, ddz, and then h3 times a3. a3 is 0, so we have 0 here. From there, it's just a matter of doing the determinant, and the final answer is 3 over rho. Now to review what we covered in this short video, first we reviewed spherical to Cartesian coordinate transformations as well as the scaling factors, and we had cylindrical to Cartesian transformation equations as well as their scaling factors. Next, we defined the gradient in curvilinear systems. So this is the general form of the gradient, del cross some scalar function phi. We applied this formula to the spherical coordinates and got this specific formula for spherical coordinates, and then I showed you the specific formula for cylindrical, and we also did examples. Next, we did divergence in the curvilinear system, and this is the general formula we have for divergence. We applied this to spherical and got the spherical formula, and then we also looked at the cylindrical coordinates and did examples in both. Finally, we looked at the curl, and there's 2 formulas you can use. You can use this one here, the Levi-Civita, but I chose to work with this determinant definition of the curvilinear curl, and we did an example here. So that's it for this video. Thank you for watching.